Hi and hello everyone. I was told to just start and greet you back from lunch. I'm Robert Jonsson. I'll be the first of two lectures between this and coffee break, in which first me and then Sebastian will show that all the structures, which potentially felt abstract or mathematical this morning, relate very directly to what we are used if you have a physics training from Dirac spinor wave functions on manifolds. Before that, I should not forget, and I will not forget to, since I'm the first external speaker, I think, or not based in Regensburg, to thank Felix, Claudia, and the entire local team who's organizing this for putting this together. I mean, thank you and congratulations also. And, oh, well, I will also use this to plug in some commercials directly, which they maybe, because they didn't do. All the material that we saw this morning and we are seeing this afternoon is presented very well in two textbooks that Felix has. That's the older one, the continuum limit of the causal fermion system. You can buy that, absolutely, and I hope you will by the end of this week, or you can find it on the archive. And also there's a book coming up just this month, or coming out just this month. It's also already on the archive by Sebastian, by Jan Henrik, and Felix. What is it called? I think, yes, it calls the fermion system an introduction, and the title goes on. Also, that one is on the archive. So for example, the material for this lecture you would find there, chapter 5.7, or in the blue book, the older one, 112 to 114. So what is this lecture about? Well, I want to connect the abstract framework that we had this morning, well, maybe it's hidden behind here right now, to this picture that we maybe have with us from spinor wave functions on spacetime, maybe Minkowski spacetime, which could look like this, right? If you think, I mean, what is a spinor wave function? Well, we think we have a classical spacetime in the background, often called M. And then if we go to a point in space-time, x and m, and we evaluate a wave function there, then what we would get, for example, for a Dirac spinor field is a 4-component complex valued vector. And these spinor wave functions we can think of as maybe sections in the spinor bundle, right? That's just what I said in words, in maths. Well, a spinor wave function will take a point in space-time and map it to a spinor that is attached there to the space-time point in the spinor bundle, which, well, maybe secretly you can think of C4, just a 4-component complex vector. But of course, the structure is a little richer than that. We typically would use the spinor inner product here for a Dirac spin 1/2 particle, the one that we used from our first QD lectures, and all from our first QD lectures. It would be that you take the adjoint of one spinor, you put the gamma 0 matrix in the middle, take the other spinor, and that's your inner product. It's an indefinite inner product with signature plus plus minus minus. And these structures, actually one can construct very naturally from this abstract framework Felix presented just before lunch. Question is how, and that's what the next 3 pages should be about. So how do we get to a picture which exactly matches this when we start from a causal fermion system, which, just to recall the definition, consists of a Hilbert space, separable and with its inner product, the set curly F of all these self-adjoint operators with, at most, in brackets I should say, n positive and n negative eigenvalues, and rho, the universal measure, whose support was the spacetime, right? We say that all points in the support of rho, which is a measure on F, that they correspond to spacetime points in our physical spacetime. Well, to get to a wave function, all you need to do is really, you pick a vector in H, and that immediately gives you a wave function. Look at this. If we take U just to be any vector in Hilbert space, then we can pretty straightforwardly find a map which picks points in the spacetime and gives us back, well, a 4-component vector, or well, a 2n component vector. That depends on, well, I will here use n to be 2, because then, of course, we get a 4-component vector, more or less. What you do is, you can take u and define the physical wave function psi u as notation as the map that just takes a space-time point and returns to u as a vector in the Hilbert space the projection of u onto the image of x. Right? X has 2n non-vanishing eigenvalues. So this thing, in effect, lives in a 2n-dimensional subspace, just like the spin space that we are looking for. And if you do that, you hold one point fixed, and you do that for all your vectors in the Hilbert space, well, then you get what we would identify as the spin space at x, which is then nothing but the image of x. Right? The image of x, again, because it has 2n non-trivial eigenvalues, is a 2n-dimensional subspace, and that is what is identified with the spin space in this picture. That's just a subspace. Now we need the inner product. And here, what we can combine is that we are working in a Hilbert space, which already has an inner product, a definite inner product, but we have x with its n positive and n negative. So here I should say 2 positive, 2 negative eigenvalues. So we can use that to define the spin inner product on this subspace. Maybe I should show this of x of h that we just defined. So on the image of x, we can define this inner product, which is when you take 2 vectors in the spin space, the image of x, well, you get the spin inner product just by plugging them into the Hilbert space scalar product with the x in the middle. And then, since x has at most n positive and n negative eigenvalues, the spin inner product has at most signature n. Right, so I'm looking here at the time, and I'm surprised myself how easy it was to get these structures back out from the abstract definitions. So do interrupt me, please, with questions if anything isn't clear at this point. This one, I just accepted this as a convention, and I mean, it can't mean much more, can it? What is the good reason for the convention? Okay, so nothing but a convention. At least this is the convention also used in the books, the textbooks, these references. Right, so now we have the spin spaces and the inner product on it, which corresponds to the spinor inner product that we know from classical physics. So that's good for one space. Now we need to connect. We want to be able to connect different the spin spaces at different points. And Claudio already also had this object in its on his slides, which is the kernel of the fermionic projector, and that will do the job of connecting different spin spaces at different points with each other by mapping them onto each other. And also we are able to express the causal action principle, which you here looked at in terms of the products and the spectrum of the products of two operators, also again in terms of this kernel. Yeah.
The regular definition of a spinner, because I mean it has to vector space that carries a reducible representation aspect. That's how I would type X is spinner.
Yeah.
So what should that have to do? If I didn't do it.
I don't know if is there deeper with the representation theory. I usually only look for the.
Why is it
definitely discuss it after Sebastian solved it, because we need now show how this spin space connects to the usual spinor spacing process. We can discuss how the spin.
As a preparation to define this kernel of the fermionic projector, we will basically just address the projector that we used before, pi x, which was the projector onto the image of x, with some fancy and suggestive notation. By calling it or upgrading it to the wave evaluation operator. Before I said, well, if you pick any u, you can define the wave function because it will map any point x to a 4-component vector. Now let's call this the map, which takes a vector and gives you a wave function. Let's call that the wave evaluation operator. So we use this symbol, psi of x, notified with a capital psi here, as the map, which takes any u, which is a Hilbert space element, a vector in Hilbert space, with a Hilbert scalar product. And it will return to you, well, the wave function, the physical wave function of u at x, which is nothing but the projection of u onto the image of x. Why this extra notation? And well, because now we want to think, or it helps, I think, to think of this map as a map from the Hilbert space with its scalar product to the spin space with the spin inner product that we just defined, so the indefinite inner product. Because when we do that, we can also look for what its adjoint is, right? So the map that would take you back from the spin space into the Hilbert space. And that one is given by you strict minus x to the spin space, to the image of x. Let's check how this works out. Well, if you take a vector in the spin space and any vector from the Hilbert space, then you can evaluate, you can start in the spin space at x, where v already lives and u is put into or mapped into by the wave evaluation operator. Then you plug in the definition of psi of x that we just used. Then you realize, oh wait, no, then you use the definition of the spin inner product, which was just put the conventional minus sign and x in the middle. At this point, you may drop the projection operator as well. X was self-adjoint, so you easily move it over to the other side. Well, and that's what we want for the adjoint. So the adjoint is minus x of s of x. So now we have a map which takes you from Hilbert space down into the spin space, the wave evaluation operator. And we have a map that takes you from the spin space back up to the Hilbert space. And we can combine them. And one way to combine them is, of course, to do psi star after psi. And what you get there is basically x. So you can express now the space-time point operator x also in terms of this wave evaluation operator like this. A quick check that this holds maybe. Well, you pick any vector in Hilbert space. You apply this map that you just defined to it, plug in one definition after the other, and see that all you've done is applied x to it. So that plays out. That's not very useful. We had x before. More important is if we combine the two the other way around, then we do get the kernel of the fermionic projector. If we apply, where am I here? Psi x after psi star, and also use different points here, then now we have a map that take you from the spin space of y to the spin space of x. And in this nice notation, it's sort of obvious, and if you check it carefully, you also find it, but I didn't do it here, that this thing is self-adjoint, right? If you want to star this and you apply the usual rules, well, oh no, sorry, not self-adjoint, but that you just need to swap the arguments in order to get the adjoint. So this is why this is what makes this notation nice. what is this thing actually if you grind it or go look deeper under the hood in terms of the operators we had before? Well, if you spell it out by plugging in the definitions, you see that pxy would be, well, you restrict yourself to s of y. The projector starts at the second argument, apply y and then project onto x. Or if you like to think about this in bracket notation, because that's where your training is maybe, then you can also express this kernel by picking an orthonormal basis of your Hilbert space and then looking, well, at the sum of these bra projections followed with the cat. At this, I'm not going to go into more detail here, but I think at this point it really smells almost like, well, a two-point function, and that this thing captures the correlations that live, so to speak, in the DRC of the vacuum, or the DRC configurations. Good. Now the thing that is left to prove or to show, and is that is left to show, is that what I said in the beginning, that you can capture the causal action principle also directly in terms of this fermionic, the fermionic projector kernel. How do you do that? Well, we had the projector as a map that well, takes you from spin space y to the spin space of x. What we need here is what is called the closed chain. I like to think of it as something that starts at y, takes you to x on a return trip and back again by composing pyx with pxy. That is a map from the spin space of x back to the spin space of x. And the claim now is that this operator is isospectral to the operator products that we need here in the causal action principle. And for this calculation, I devoted the page coming here. Let's look at this together, how the objects we just introduced and the operators play out together. So we defined the closed chain as this return trip from x to y and back, plugging in all definitions. That's all what I did. In fact, plugging all the definitions, this is pyx, this is pxy. Well, it's really hard to see. I should point like this maybe. Right, this is the definition of px, and then we said before what these operators are. So here we have the adjoint. Well, it's really term by term just put together. And if they are there following each other, we see that we can drop the projector in the middle because y comes right after. Also, the two minus signs cancel out. And we are back at this thing, which basically is the product of y and x, just restricted to the spin space and projected back onto it. So now with a little, well, either you already at this point think of matrices and are convinced now these are going to be isospectral, then you're fine and done, or maybe satisfied for the purpose of this lecture. If you want to look more critical and what the work behind, or what the idea is to show this, is that you can realize that, well, y and x, because they only have finitely many eigenvalues, they map a finite dimensional subspace of the Hilbert space onto itself, right? For example, what we could use would be the span of the image of their product and the orthogonal of the kernel. So then, though, we can represent this operator as a matrix on this subspace and find that its eigenvalues are, of course, the roots of the characteristic polynomial if you restrict this operator to that finite subspace here. And now the nice thing is that all the coefficients of the characteristic polynomial of that matrix you can express as functions of traces of powers of this operator. So what I put here. If you know this for, well, p up to some finite boundary, same of the dimension, I suppose. Then you know the characteristic polynomial. And here it's already clear that these coefficients then, of course, are the same for yx as they are for xy because of the cyclicity of the trace. But now, so from these objects, for all the p's, you get the eigenvalues of xy that you were told this morning go into the causal action. But then if you look at the characteristic polynomial, or rather it's the coefficients of the characteristic polynomial that we get for this closed chain that we just defined up there, well, we would get those coefficients by taking traces on the spin space. But if we map it through step by step, we see that actually the trace of the pth power of the closed chain is the same as the trace of the pth power of the xy product. Hence, the characteristic polynomials will be the same. Hence, they have the same spectrum. And so you can use in the action, your causal action, instead of the spectrum of xy, directly the spectrum of this product of the closed chain, which, well, may be more accessible because you directly would construct it as 4x4 matrices, and also which directly links to objects we know when we work with Dirac fields in Minkowski spacetime, as Sebastian will do next. This is, I think, the first time that I'm giving a talk or lecture where I run into the opposite problem of not going over time, but I'm way under time. But this was the material that was assigned to me. But maybe that works well. But you could, I mean, we could review this and ask questions about this, or you take the causal structure now that we didn't get to earlier. But this is what I brought along.